today we will learn something about the Bayesian thing. Okay, Bayesian learning. Okay, so this Bayesian learning is nothing but a kind of learning which learns in the form of Bayes theorem, basically. If you guys remember the Bayes theorem, can anyone tell me Bayes theorem, conditional probability? Do you guys remember from the machine learning?
Basically, with every iteration, it basically takes the learning from the previous iteration and tries to apply it for the next iteration. So
Exactly.
that is how the Bayesian works on the experience basis.
Correct.
And
Yeah.
then you cannot have any, bandit policy or anything to segregate or cut off the ones that are underperforming in this scenario.
Hmm. Okay. Okay. Great. So in Bayesian learning, in case of deep learning, basically, we can divide it in two parts. Okay. The one way of learning, one way of classification in Bayesian learning in deep learning is called Bayes minimum error classification. Okay. And the second way is called Bayes minimum risk classification. There are two things here, and we'll learn these two terms in detail today. We'll try to derive the formulas for Bayesian minimum error classification, as well as we'll try to derive the formula for Bayesian minimum risk classification as well. Okay, and we'll see in details how they work. Before I move to the details of Bayesian minimum error classification and Bayesian minimum risk classification, since I had told you that please go through the differentiation rules. Okay, if some of you, any one of you have looked at differentiation, how differentiation works and what is that, how chain rule works and all. Before I proceed, there are a lot of uses of differentiation and chain rule differentiation. Okay, so we'll see, for example, a given function y equals to 5x to the power 3. Okay, this is given like y equals to 5x to the power 3. How will you find the dy by dx? Any idea, guys? Do you guys remember?
10 square.
15x square.
15x.
15x
Square.
15x square. So it means how this is a constant. This 5 is a constant. So
Yes.
5, we'll have to just write 5. And inside, we'll have to write this is in the form of a x to the power n, right? And this takes the form like a, means whatever the constant value is there, we'll write as it is, and we'll just write n into x to the power n
Minus 1.
minus 1, right? And it will become 5 into n. N is nothing but 3 into x to the power 3 minus 1, which is 2. So 15x square. This is nothing but my differentiation. Okay. Are you guys aware why are we using the differentiation? Any idea? Why do we do the differentiation? Any idea?
So basically to measure the rate of change.
Rate of change, great. Okay.
If you
So
have
why do we
trouble
need the rate of change in machine learning and deep learning?
Any
Machine
dependent or
learning.
independent variables, if you look at,
Mhm,
so the change in the independent variable, how will it
mhm.
impact the dependent variable in simple terms? So
Okay.
if we want to have a measure or a pattern look at it, that's what we try to do in differentiation.
Okay. Great. So the change. Now, when we find the differentiation, right, we also say we have to find the minimum value or maximum value. Correct or not? We have to find the minimum value or maximum value. Have you heard about the minimization of the error? Suppose we have something like minimum, this one, yi minus y hat square, and we take like 1 by 2m. Okay, now tell me, this is a loss function or error function for, say, linear regression, right? We have to minimize the error. In case of linear regression, say, we have something like this. Suppose this is the regression line, right? Why this regression line? Given multiple points here, why only this regression line? Why not this one? Why not this one? Why not this one? There may be multiple regression lines here, right? But why are we choosing any particular regression line like this one, for which the equation will be y equals to mx plus c? Why? What is the reason behind choosing this line?
Where there is the least residual uh, thing, right? I mean, the deviation is the least, or the where most of the points aggregated towards the average point, mean point. That is what we try to achieve from the line that we want to draw.
Correct. Means we have to find the line of best fit, right? Line of best
Yes.
fit. Now, when someone asks you to find the line of best fit, what is the definition? The definition is like you will get the minimum error or minimum residual. Correct or not? What is the minimum? What is the error, by the way? Error is given by y minus y hat square, 1 by 2m. Why do we take this 1 by 2m, guys? This m is nothing but the average error we are finding, right? 1 by m. Now, why 2? Just to simplify the problem, simplify the output. Because when we will find the differentiation, it will be like 2 into something, right? And this 2 will cancel each other. That's it. No other reason. Okay. Now, when we find the minimum error, it means we are talking about some minimum value of any given curve. Correct? When we are talking about minimum value, say the error function, the residuals are like this one, or the error is like this one. What is the minimum value of error? This is the minimum value of error. Now, how will you find this error value? At what value of x, at what value of y, or at what value of any given parameter, your this one, your error will be minimum. And that's where this differentiation comes into the picture, right? We have to take the differentiation. We have to take the differential of the error function, so that we'll be finding the minimum value of the error. At what point the minimum value of error is there, and that's where we will try to find the line of best fit based on the minimum error. Okay. Now, that's how the the use of your differentiation comes. Okay. Now, this one is one of the um, functions, differentiation. What is the differentiation of this guy? Given y equals to x square plus x cube, what will be the dy by dx, guys? Any idea?
2x plus 3.
2x plus 3x square, right? We are applying the same formula. Okay, so dy by dx will be equals to n into x to the power n minus 1. This is the formula where y is given as x to the power n. Okay, now we can apply when something like x to the power m plus x to the power n, and we have to find the dy by dx. How will you find that? You can easily find like dy by dx of x to the power m plus d of x to the power n by dy. You can separately find the differentiation and you can add them together. Similarly, here we did this now. Clear, everyone? Do you guys have any doubt here in differentiation?
No.
No? Anyone?
No.
No? Okay. Now, no, then what will the differentiation of this kind of thing? Cos x into sin x. So, this is in the form of product. So, suppose fx into gx. Two different functions have been given. One is cos x, another is sin x. Right? And this kind of differentiation can be found by using chain rule. How? See that. This product rule says that the derivative of f and g, two given function f and g, is nothing but first keep the first function constant as it is, and find the differentiation of gx and multiply with f. The second time, find the differentiation of the first function f as f dash and keep the second function constant and multiply them. This is called product rule or chain rule. Is it fine? So here f is given as function in cos and g is given as function in sine. What will be the differentiation of fx? Cos x. It will be minus sin x. What will differentiation of the second one? Sin x. It will be cos x. So we have to find the derivative of cos x into sin x. How will you find? Right? Cos x, the first term will keep it as constant, and find the differentiation of the second term gx. What is that? Differentiation of sin x equals to cos x. So cos x minus y minus, it will be plus only, but I'll tell you y minus. Differentiation of first term cos x is minus sin x, right? So plus minus minus sin x multiplied by the second function. What is sin x only? Sin x. So resultant one will be cos x square, cos square x minus sin square x. Okay, this is nothing but this is called chain rule, guys. Okay, so we can find du by dx plus, sorry, dy by du plus du by dx. Okay, if given two different functions, like in case of x and u, then first we will find the differentiation of y in terms of u, and after that again we will differentiate u in terms of x. Okay, so this is the basic differentiation rule in calculus. Okay, now similarly here, as I told you, if x, y, z, a function is given in terms of x, y, and z, right? Now, if you have to find the differentiation of this one, partial differentiation of this one, how will you do that? By using chain rule. Simply, you can do it by using chain rule. First, we have to find the differentiation of this whole function with respect to x. With respect to x, how much it will be? 4x cube minus 3yz, because in this case, y and z will be constant. Similarly, if we find the differentiation of this function with respect to y, then all the things will be constant except y. So this will be constant, x to the power 4. So this will be 0. And 3xz, because differentiation of this function f with respect to y. How much? This function 3xyz. Okay, this will be 3x and z. Okay, x and z will act as constants. Okay, now again the differentiation of the function f with respect to z minus 3xy. So this is called the chain rule, basically the partial differentiation, basically, and we are trying to solve the partial differentiation using the chain rule. Okay, so what will the final differentiation of x, y and z? We have to find df by dx plus df again by dy plus df by dz. This will be my final partial differential. Some basic probability concepts. Okay, so before we start, okay, with what Bayesian learning is. Bayesian learning is nothing but two types, as I showed you: Bayesian minimum risk classifier and Bayesian minimum error classification or classifier. Okay, so before I start, I want to give you a heads up with some basic rules of basic basic probability concepts. Okay, so basically, when we talk about the basic probability concepts, okay, we are calculating the class conditional probability density functions. Okay, so suppose any given thing. So in basic probability rule, we write this probability of A and B will be what? According to the Bayes theorem, probability of A given B multiplied by probability of B, right? So this A here in our case are nothing but these feature vectors X, and this B is nothing but some given class omega I, right? So probability of X given omega I multiplied by probability of omega I will be probability of omega I given X multiplied by probability of X. According to the Bayes theorem, guys, this is nothing but your conditional probability, right? And from conditional probability, we derive the Bayes theorem like this one. How do you derive this one? Shall I derive, or is it fine for you guys? How did we come from this one to this one? Is it understandable for everyone, or shall I derive? What do you say?
Please derive.
Okay, derive. So what is the probability of A given B?
Probability
So
of
basically,
A and B, probability of B.
probability of
B,
A and
A
B,
and B by probability of B.
A and B by probability of B. Great. Okay. So what will be probability of A and B?
Probability of A by B multiplied by probability of B.
Not A by B, it's probability of A given B.
Given B, okay.
Yeah, into probability of B. Okay. Similarly, what will the probability of B given A? It will be the same probability of A and B divided by the marginal probability of A this time, right? So similarly, probability of A and B can be given as how much? Probability of B given A into probability of A. Fine, everyone?
Yes.
Is this fine? Okay. So this is equation number
Yes.
1. This is equation number 2. And these are nothing but conditional probability that I have written here. This is the conditional probability, same conditional probability, right? Correct. Now from this conditional probability, I am deriving this one. How? Since both of them are LHS are same, you can equate the RHS value, right? So probability of A given B multiplied by probability of B equals to probability of B given A multiplied by probability of A. Is it fine? The same thing I have written here, right? Can you see here? Probability of B given A multiplied by probability of A. Probability of B, this is a B given A multiplied by probability of B. Okay, equals to probability of B given A multiplied by probability of A. Same thing I have written here, right? Similarly, this is basically the base theorem, and you can derive probability of A given B equals to probability of B given A multiplied by probability of A divided by probability of A given B. Sorry, probability of B. Okay, this is nothing but your base theorem. Do you guys remember this base theorem? Everyone? And that's how we are writing here. Same thing. Yeah. So this kind of thing, when see the term, now we will talk about each of the terms. Okay. So the term px given xi, sorry, p probability of x given some class omega I. This is called class conditional probability. Class conditional probability. Okay. And in terms of function, if it is defined in terms of function, this is called class conditional probability density function. This probability of omega I means probability of occurring any feature vector x into any given class omega I. This is called a priori probability. What is the probability of omega I? Class cat, class dog, class horse, etc. This is called a priori probability. Okay, and we are actually interested in finding the posteriori probability. What is posteriori probability? This one. Probability of omega I given x. It means what is the probability that a certain image will belong to class cat given some features. The same thing here. This is nothing but same thing. What is the probability of omega I? What is omega I? Class. Any class. Say cat, dog, horse, anything. What is x here? X is nothing but your feature vector. Okay. So what is the probability of omega I given x? That's what we are actually interested in this portion. Okay. Clear everyone?
Yes.
Any doubt? No? Yes?
No doubts.
No.
Okay.
Yeah.
So from here, can we write, if we are interested in finding this probability of omega I given x, so what will be that? We can write probability of x given omega I multiplied by probability of omega I divided by probability of x. From this equation, we can write that. We can find this one. Probability of x given omega I multiplied by probability of omega I divided by this probability of x. This is what we are interested in, right? To find. Okay. Now, this probability of x, the denominator part, probability of x, the denominator part, can be ignored. Why can it be ignored? Because we are actually trying to find the probability of different classes. Different classes. Say we also have to find what is the probability of omega j, a given feature vector x. Given feature vector x, what is the probability that it will belong to the class omega j? We shall again be given as probability of x given omega j multiplied by probability of omega j divided by probability of x. When we are comparing these two, right, these both the denominators are same, correct or not? Then we can ignore that denominators. Okay, so that we can compare only the numerator parts, because divided by some constant, this will be a kind of constant in both the cases. For example, the probability of x is 0.01, so it will be 0.01 in both the cases, right? The feature vector x will be same in both the cases, and we are interested in finding in which class this feature vector x can be classified, whether omega I or whether omega j, which class, right? So we found the class conditional probability here, and we are trying to compare them. While comparing, we can ignore the denominator part x. That's fine. Okay. Now, is it fine, guys? Now, this probability of x is also given as summation of probability of, say, x given omega I into probability of omega I. Okay, for all I, for all the values of I, this probability which we are ignoring at this time. Okay, now just say we have two probabilities here, values, probability of omega I given x and probability of omega j given x. It means probability of x being classified to omega I and probability of x being classified to omega j. And now in any case, say if probability of omega I given x is greater than probability of omega j given x, then what will you find? Then this x will belong to omega I. If the probability of omega I given x will be greater than probability of omega j greater than x, it will be given, yeah, but omega j given x, then we can easily say that this x belongs to omega I class, this class, right? Now see, we have the distribution like this one, the probability distributions like this one. Suppose in the x-axis, this is the x-axis and this is the y-axis, for example, and in the x-axis I have all the feature vector x's. Okay, now in the y-axis I have probability of omega I given x. Okay, now just think, I have, since since we are doing, say, binary classification of images, right? So there are two possible classes, okay, omega I and omega j, or say cat and dog. Both the classes have some possibilities given some feature vector x. Okay, now just think here that, say, I have some probability distribution like this one. Okay, this is for, say, omega I, and there will be some other class also. This is, say, omega j. Now tell me, guys, given any value of x, say here I have x, any feature vector x, because in the x-axis we have the feature vector, right? So given any feature vector x, I mean given any feature of any image, okay, x, there is a probability, there is chance that it will have the higher probability that it will become to omega I, correct? But there is also few probability, very less chance that it may also belong to omega j class, correct or not, guys? Yes or no? Do you guys agree with that?
Yes.
Because
Yes.
when we find the probability in any say logistic regression only, right? Okay, so in a logistic regression, when we say 0.82, right? So again, 0.28 is the probability that it will belong to some other class also. Since we set the threshold there, correct or not? We set a threshold of say 0.5. All the probability values greater than 0.5 will belong to class 1 or else 0, 0th class. And so this one will belong to, this observation will belong to class 1, right? We set the probability rules like that. Similarly, here also, since we have two classes, those two classes will have some probability distributions, say omega I and omega j. Okay, for any given feature vector x, there is a chance, there is a high chance that it will belong to few class say omega I, but it is having, it is also having some chances, some probability that it is also belonging to some class omega j, but that will be lesser, very less as compared to omega I. And then there is some error made in that. I mean, whatever the difference in those probabilities, that we are calling it as error. What is the probability? For example, if 0.8 is the probability of becoming or classifying any observation, given observation into cat, then 0.2 is nothing but my error. The probability which it is calculating that the same feature vector x will also have the probability of belonging to some other class dog, and that probability, the same probability, is nothing but my error only, correct? So in logistic regression, if we have say sigmoid function, have you heard about this one, sigmoid function?
Yes.
Yeah. So what was the probability of x given there, or say not probability, say y? What is the y there? 1 by 1 plus e to the power minus x, right? What is the x here? X, it is the just the linear predictor,
Y is equal
beta
to
naught plus beta 1 x1
Correct.
plus beta n xn. It is just a linear predictor, right?
Yes.
And this some function px equals to y equals to 1 by 1 plus e to the power minus x, right? Now, when you write this kind of equation, it means we have something called odd, right? P by 1 minus p, right? So when you put the values in this equation, all the values in the equation, when you put the value, when you put the values of p and 1 minus p from this equation, you will get the odds of the probability, right? And after that, we derive the logit function. If you guys remember, s will be e to the power beta naught plus beta 1 x1 plus beta 2 x2 plus beta n xn. And when we take the log of this s, means this e will go off, and that's why it becomes linear. That's why we call it as logistic regression, which becomes linear in nature. And this log of s, it will nothing but it will give you the probability value. So basically we derive there, right? So by by calculating the we are basically interested to calculate the probability also. In case of logistic regression also, we are interested. So for any given feature vector x, say x1, x2, x3, and y, right? There are different features, say x1, x2, and x3. And for any given features like x2, x2, x1, x2, x3, we are interested to find the probability of y. What is the probability that it will belong to either 0 class or 1 class? That we have to find it, right? So first we will try to find the probability. Suppose we got the probability at 0.2, right? So it belongs to class 0. If it is now, if the probability is coming at 0.8, so it will belong to class 1. In case of binary classification, we set a threshold on the probability. Similarly, random forest also we do similar kind of thing. Random forest will also give you probability in cases of classification. What is the probability? It will give you probability only, right? Suppose for any given x vector on x-axis, this is the x vector on the x-axis, correct? There is still a chance, right, that it may belong to some other class, say omega j, this omega j. There
Correct.
is a chance, right?
Yes.
As well as it will also belong to some class omega I.
Yes. It's our job
Correct
to
or not?
classify.
Correct?
Yes.
It's our job to classify,
Hmm.
right? Now, in case of logistic regression, we had only two classes, and based on the threshold value, we used to classify. So if the probability value is greater than 0.5, it will belong to class 1. If it is less than 0.5, it will belong to class 0. That's what we used to do there. Correct or not?
Correct.
Yeah. Now, here there will be multiple classes. I am showing you on the with the help of only two classes, say omega I and omega j, for example. Okay. Since the corresponding value of this omega I for any feature vector given any given feature vector x on the x-axis, the corresponding value of omega I is greater. Can you see here? It's greater, right? Than this omega I. In case of this image classification problems, see, we'll be having multiple nodes. So, for example, in the internal nodes, output node will be having two nodes here. And these two nodes will give you, say, this is cat and this is dog. Say, this x feature vector is belonging to cat. So, it will give you 0.8. But it will also give you some probability of dog, which will be 1 minus probability of cat, which is 0.2. Correct? Now here we don't set the threshold and all. Here it is all decided by your network, your algorithm. Okay, so here as you can relate this problem here, any feature vector x, if you pass, and it will give you some probability value. Suppose the probability of occurrence, say for the cat is 0.8, which is obviously greater 0.8, but at least but there is still some chance that it will also belong to some class dog. Correct or not? There is some probability for dog also. This is the 0.2.
Yes.
Correct? Got it till here? So the feature vector x belongs to omega I. Why? Because the probability is more. Correct? But there is still some error that it may also belong to this omega j, as I have shown here. There is some still error 0.2, right? And what is the probability? As you know, probability is nothing but area under the curve. And that error is calculated by area under the curve here also. And this probability, the misclassification probability, is nothing but your error. Okay, so this probability of error given any feature vector x is given by this minimum of these two probabilities. Probability of omega I given x, comma, probability of omega j given x. This is nothing but the error. Whatever the probability that you are finding, which tells that it will not belong to the class correctly, that is the error. And that error, we are finding it by taking out the minimum value from the classes. They say, as I introduced, so this field is evolving day by day. This deep learning field is evolving day by day. Correct? Now, suppose I give one algorithm today, right? Now next day tomorrow, someone will give some better algorithm tomorrow. Someone will give more better algorithm a day after tomorrow. It actually keeps on evolving. The algorithm or the mathematics, all these things, or basically the implementation part of mathematics. So we have some set of mathematics, some algorithm, some set of algorithms in mathematics. By using those algorithms, we are trying to implement those algorithms in real time by deriving some few more, algorithms, right? Now, what will happen? Someone else will come and they will use all those algorithms in some different way. They will add up some algorithm, they will remove some algorithms, they will again use all these algorithms in different way, and they will come up with some new result. This will be evolved one. So the similar kind of problem, I can solve the similar kind of problem in some efficient way, the more efficient way, the most efficient way, right? So there are different methods basically for the classifications here. Okay, and it is a very previous things. Okay, so since we have started from the very basic, we are looking at each and every aspects of deep learning. Will be touching. So yeah, okay. Now coming to minimum base minimum risk classification. Okay, we know how to find the probability of error given x. So in base minimum error classification, basically we were interested in finding the error of the classification. What is the error that your model or that your algorithm is making while classifying two classes? That's what we are more interested in. Probability of finding the errors given some feature vector x. Okay. Now here, this base minimum risk classification, you can say, is more general form of base minimum error classification. Correct? In base minimum error classification, we have considered only a set of classes. Correct? Suppose I, and this I will belong. I'll be suppose I need to write. Okay. Say we have omega I here. This omega I will take this I will take the values as 1 to C. Okay. So in case of this base minimum error classification, we considered, what did we consider? Only set of classes I. Whereas in base minimum risk classification, okay, we will consider the omega I, this fine, as well as we will also take a set of actions which is represented by alpha j, and this j will vary from 1 to say k. We will take some feature vector x, which will be say d-dimensional feature vector. Okay, so when we take a set of classes, this omega I is nothing but set of classes, right? This
Just
alpha,
classes is okay. Yeah,
okay, set of actions.
actions. Yeah.
Okay, set of actions. So basically, when we take a set of classes with some set of actions, then the loss function is given by lambda, and which is like alpha I given omega j. when we take some set of classes, say omega j, and some set of actions, say omega I, then the loss function loss is given by this lambda alpha I given omega j. It will be more clear. Okay, wait, not worry.
Now this loss function formula changed or what here?
No, it is not changing. Yeah, definitely it will change for each and every
Yeah,
algorithm,
because
each and every
okay,
topic, right?
okay,
Loss function for logistic regression, the loss function for linear regression, the loss function for random forest, everything will be different.
change. Okay,
Correct.
fine.
Yeah, based on their parameters, right? Trainable parameters and all. Okay. Hmm. Now consider, so in Bayes minimum error classification, when we try to predict a given set of feature vector x. Okay. So for example, now when any given feature vector x is given to you, in Bayes minimum error classification, what we try to do? We try to predict that a given set of feature vector x, this x, okay, which class this x belongs to. Correct or not? Which class again in omega I it belongs to. Correct?
Yes.
Am I good? Yeah,
Yeah.
that's what we used to do. But in Bayes minimum risk classifier, this form, this way, we assume that when we take some actions alpha, any action, say alpha, to predict a feature vector x to be classified within a set of say classes omega I.
Hmm.
Okay, then there is a risk involved in that prediction. When we take some action, there is always some risk involved. So this algorithm will take some actions. Actions means what? It will take some actions. Actions means what? It will try to predict. It is a kind of action only, right? When it is predicting something, when it is calculating something, there is always some risk involved in that. So here also there is a risk involved in that prediction, which is given by this Bayes minimum risk classifier. So just assume any feature vector x, okay, okay, and some action taken xi, some feature vector x and some action xi. Okay, then the risk involved is given by r. What is the risk while taking any action xi given some feature vector x? This risk is given by this lambda of omega alpha I given omega j multiplied by probability of omega j given x for all value of j. Now tell me, we are trying to find the risk while taking any action omega I in while classifying x into omega I. So we are taking some risk alpha I. Okay. Now tell me, when you are taking some action given some feature vector x, always there is some risk involved. What is the risk? So risk is calculated when some action alpha I is taken given some value feature vector x. The risk is given as this alpha, the loss function, while taking this action alpha I given some omega j, some other classes. Because what will be the risk? The risk, you cannot say alpha I, why I'm taking the action alpha I given some omega I only. The risk will be, this is nothing but the loss, right? Can you see? This is nothing but the loss function, right? What will be the loss? When it will belong to some other class, that will be my loss, right? when it will belong to the same class, then we cannot say this is the loss, right? This is the loss. For example, lambda is the loss, and alpha is the action taken, and omega is the class, and omega j is also the class. Then we cannot say that this, while taking the action xi, and when it is classified as omega I only, then there is no loss. When it is classified as omega j, then there is a loss. There is a error, right? That's why we are calculating the loss lambda while taking any action alpha I given some omega j class multiplied by probability of omega j given x. When you just sum it over all j values, then you will get the risk. Let's take an example. Okay, suppose if given feature vector x actually belongs to class 1. Okay, correct or not?
Yes.
Okay, now when it will actually belongs to class 1, then we have a total c classes ranging from 1 to c. Okay, then the total risk involved in predicting the class 1 will be equal to individual risks for all the classes. Okay, and in that case, according to this formula, we have to take the summation by using the formula given here for the risk, and we take the action where the risk is minimum. So this action, this loss lambda, while taking any action omega I given this alpha I given omega j equals to, we can write it as alpha lambda ij. Lambda ij means loss while taking any action alpha I given some class omega j. This risk will be minimum, okay, when I equals to j. Just assume, we are assuming it. So in
Just
this
a
case,
question. Sorry.
yeah,
Till now, actually, for misclassification, we can't find only error because till now we always calculated the error. So I
mhm,
think now only we introduce this loss function. So calculating
mhm.
the error, we can't find like total error or something here. Means I might be a very basic question, but I'm just thinking
Calculating the error.
error for misclassification.
Yeah. So yeah, definitely we have, since we are finding the error, I mean say y I minus y hat, as I said, we take the summation, right? We do this only, right? We
Yes.
take the summation of all the errors, and this is nothing but a function, and that's why we are calling it a error function or loss function. And that we need to maximize or minimize whatever we want to do. We have to minimize in our case, okay? Similarly, in this case also, we will calculate error only, and we have to minimize the error. Okay, so I'll introduce with all the error functions, all the loss functions in coming classes. Okay, there will be a lot of error functions. Don't worry. Okay, loss functions for each and every algorithm, for each and every method of classification. I'll introduce different error functions. Okay, see. uh, okay, when we train some algorithm, okay, then every time the training parameters will be involved. Agree with that? Every time some training parameters will be involved. Correct or no? I mean, correct.
Yes.
Yes.
For example,
Yes.
when you are training some, say, decision tree, right? And when you are training some decision tree, it means, uh, or say random forest, then it means number of trees you have to decide, correct? Some training parameters, some hyper parameters that you need to take care of. Suppose we are training a decision tree, then we have to take care of say complexity parameter C, right? How you will prune the tree, when you will prune the tree. All these parameters are responsible for making either more error or less error. Based on that only, your error will be decided. When will you be able to calculate the error? Based on all these things, your classification will happen or regression will happen. When classification will happen or regression will happen, there are two possibilities only, whether correct classification or misclassification. Then when misclassification, then you are interested in finding the error. Why did we do misclassification? When did we do misclassification? At what values of different training parameters we did the misclassifications? And what should be the optimal value of training parameters to get the minimum error or no error? No error is definitely not possible, but yeah, minimum error. How will you find that? Right? So, with respect to different parameters, actually, we have to differentiate the error. When we talk about the error, we have to take some error function as well. The error will not be a single error, correct? It will be a function of errors, means it will be defined by some function. Every curve, for example, if you take each and every error from all the observations, it will form some curve, and when it will form some curve, then it is continuous function. It is continuous curve. When it is continuous curve, then it will also have some function, and that function we are interested in, so that we can minimize those functions to get the minimum error possible. But at what point, that is again defined by your training parameter. At what value of weight the error will be minimum? At what value of number of trees your error will be minimum? What value of number of trees shall I select? What value of complexity parameter shall I select to get the minimum error possible while classifying the classes or observations using the random forest or say decision tree, anything. Okay, so that's what we are actually interested in. And there are n number of algorithms that can be used to solve a single problem. And in what cases shall we use those algorithms, that we need to study and that we need to learn. Now, I will tell you that for the previous, 7 days, for the last 1 week, any store's sale is given as 100, 200, 200, 200, 500, 600, and 100. They are the sales for 7 days. The very simplest form to find next 1 day salary, sales means tomorrow's sales. Just take the average, mean. This is one of the methods in time series. Just take the mean and tell tomorrow will be the sales of this much. But someone else came and he said, no, we should not take only the mean. We should take other parameters also into the picture. And he introduced some other way to forecast. Similarly, here in case of deep learning or machine learning, any field, okay, since I said it is evolving, right? So someone else will come and say, no, this method has some issue. We are not getting maximum accuracy. We are getting more error, right? There are some few problems in the methods. What we need to do? So we need to introduce some different thing, some different algorithm, right? So talking about this Bayes minimum risk classifier. So as I said, when there is a risk involved in predicting any class, say class 1, Okay, this risk will be equal to the individual risk for all the classes. And so we need to take the summation of all the risks possible. Okay, now here I am telling that the loss, the risk is given by the loss multiplied by the probability. The loss multiplied by the probability, this one. So when I say loss, suppose the loss is given by alpha I given omega j. The loss while taking the action alpha I and given some class omega j. And I am representing like this one, lambda ij. The risk will be minimum, I'm saying. I'm assuming the risk will be minimum at I equals to j. Okay, so I'm assuming here that alpha ij will be 0 when I equals to j, and it will be 1 when I is not equal to j. Okay, please don't ask me why, because this is the assumption. In mathematics, we have to assume something sometime. Since we have assumed that lambda ij equals to 0 when I equals to j, and it will be 1 when I not equals to j. So according to that, the risk that we have, the risk function phi given x, that is actually given by lambda ij. Instead of this one whole thing, I am just writing lambda ij into probability of omega j given x that we had defined for all value of j. Can we also write this one as summation of probability of omega j given x for all j, for all uh, I equals to j, or say j equals to 1, ij equals to I. Since we have assumed I equals to j, in that case this lambda ij will be 0. Sorry, for it will be 0, and for I not equals to j, it will be 1. The value of lambda ij will be 1. When we have lambda ij where I equals to j, then the entire risk will be 0. Definitely it will be 0, right? When your class I, when you are saying the class I is nothing but class j, it means lambda ij will be 0. It means you don't have any risk, right? And when you are saying the lambda I, the I is not equals to j, it means we are saying the lambda I value is say 1. We are assuming it. And in that case, we have this formula of risk. Now we can also write this risk while taking any action alpha I given any feature vector x equals to 1 minus probability of omega I given x, not j. 1 minus, I'm saying. So from here we can say that the risk involved, which is given by r alpha I given x, will be minimum when this probability of omega I given x will be maximum.
So this should be 1 minus summation of all I, right?
Yeah, correct. You can do that. Summation only, yeah, for all I. That's fine. So see here, when you are saying the example, okay, I will say this is more kind of theoretical. Okay, so we just need to interpret the formulas for time being. Okay, now we will say how these things will be used. These are the concepts. These are nothing but the concepts. Okay, now when taking some example, for example, just take that you are trying to classify any given observation as, say, lone defaulter or not lone defaulter or non-lone defaulter, whatever. Okay. Now, when some algorithm is doing that classification, it means there is always some risk involved while doing the prediction or while doing the classification. There is some risk involved. Risk involved means what? What is the kind of risk involved? The kind of risk is, we said that, and also see, there is some kind of error involved. Just put it very simple. There is some kind of error involved in that. When we talk in terms of error, okay, we'll have to calculate the error function. We'll have to calculate the error function. That's it. Loss function. Okay. Now, while calculating the loss function, you are done. Means you found the minimum error, or say whatever the error you want to do on the error, you did that. I am telling that why take the error? I am just generalizing this concept called error, and I am telling there is some risk involved, and risk is nothing but your error only. It's a kind of error only. Risk means what? Risk, when you are performing some task and there is some risk involved, risk means what? Some error which will not let you perform this task. So similarly, here also in case of classification, images or say lone defaulter or non-lone defaulter, there is always some risk involved. There is some always error involved while predicting the features into classes. Now, I am saying the error, see, now I am interested in the risk, calculating the risk. What is the risk? And how, what will the maximum risk? What will be the minimum risk? Right? At what value of something the risk will be minimum or maximum? I'm more interested in that error. Now, come to that point. When I say there is some risk involved, and when I said when we take some actions, means when we start predicting, this is a kind of action. When we start predicting something, means we are performing some action, or your algorithm is performing some action. And when some action is performed, that point only some error will be made, and that will be accumulated at the end of the prediction, right? And that accumulation is given by some summation. Okay. Now consider that while taking the action, we can also define some loss function or error function. Okay. And that error function, okay, will go off. We'll just take that error. Okay. Or make it more simpler, that error function is some error function. Say in case of your linear regression, we take yi minus y hat square, right? And we're taking this summation. This is nothing but your error function or loss function. Similarly, by using this loss function, I will derive something else. I will derive the total risk involved, or I will derive the minimum risk involved. What will be the minimum risk possible in classification, in prediction? Okay, and that's what we are doing here. We are assuming something that, say, if we are trying to predict cat and the actual value is cat and the final value is also cat, right? Then what is the loss? The loss will be 0, right? And that's why we are saying, what is the loss here? In case of I equals to j, we are saying this loss will be 0. We are also assuming this loss will not be 0. It will be 1. When I is not equals to j. And based on this loss function, what I am doing is I am deriving the total risk involved. And now after that, I am saying that the total risk is given by probability of omega j given x. Means when we are trying to predict any given observation, when we are performing some action I given some feature vector x, it means we have to classify this x into I. But actually what it is happening, we are getting the risk of what is the probability of getting omega j given some value x, means the risk of prediction of this one. It means when we are predicting some class into I, but there is some probability that it will also get predicted into j, this is my risk. And that's why we said there previous thing also we were saying the same thing in minimum error classification. And when I say minimum risk classification, it is just a generalized form of minimum error classification, nothing else. Here also we are trying to find a risk. We are trying to find a what do you say, the error. The risk is nothing but the error only, kind of error, right? We are just generalizing the term, means we are just giving it some different name, risk. Okay, because someone had done that, and that's what we are studying here. Okay, and when we are saying that the risk involved while taking some action xi to given some feature vector x is given by probability of omega j given x, that we derived here, that we saw here, then we can also write this risk will be minimum. When it will be minimum, then the probability value of this one omega I given x will be maximum. It means when you will try to predict the class I into I, that probability will be, when this probability will be maximum, then we can say the error will be minimum. And that's what we are also saying that here. While taking some action xi given some feature vector x, it is also given as 1 minus this one, this value. Sorry, 1 minus omega I given x. Probability of omega I given x. Right? And when this probability of omega I given x will be maximum, this will be minimum. The risk will be minimum. And this is called Bayes minimum risk classification. Now, after that, since we have two things here, Bayes minimum risk classification and Bayes minimum error classification, what we will try to do now is we'll try to find, or we'll try to discover some function. Okay, we'll try to discover some function gix, which will decide whether an input feature x will belong to which class, class omega I or class omega j. Okay, now tell me one thing, guys. From the minimum risk classification, the minimum risk involved is given by this one. While performing some action alpha I given x, it is given as probability of omega I given x according to the Bayes minimum risk classifier. Okay, so to maximize the risk, we have to minimize the value of to minimize the risk, we have to maximize this term, maximize. Correct? To minimize the risk, we have to maximize the value, right? So can we give this a different form? It means we can give a different form of this. It means the entire value of this one should be maximized. I mean, this value maximized. So to minimize the risk, we have to maximize this value. In general term, we can write maximize. One second, I think I have made a mistake. It will be minimize only, okay? To minimize the risk, we have to minimize the whole function, this value. We have to minimize the entire risk. Right? Now, yeah, is the risk only that we derived here. Yeah, the same risk. Okay. Now, can we give this form? Can we give this function different form or not? Yeah, we can do that. So can I also say, to minimize the risk, I need to minimize minus of this term. Am I correct? To minimize the risk, I need to maximize this value. Then only it will be minimized, right? Overall. So to have a function for which the maximum value of this function will decide that the input feature, any given input feature x, to belong to some class I. The function can be given by two approaches here. Okay, so I said to just to have a function, any function, for which the maximum value of that function will decide the input feature vector x to belong to some class. It means, suppose I have any function, say gix, and gix will have some value, some function value, some function gix if I have. The maximum value of this function will decide whether the input feature vector x will belong to which class, I or j. Okay. Now, according to the, we have seen the Bayes minimum risk classifier here. According to the Bayes minimum error classification, okay, we can also define some function gix. Probability of omega I given x. And this gix, we can also write it as probability of x given omega I multiplied by probability of omega I. Okay, or this is the one of the way, or according to the Bayes minimum risk classification, the gix can also given by minus of this r alpha I given x. Any two function can be used according to the Bayes minimum error classification or Bayes minimum risk classification. In both these cases, Bayes minimum error classification and Bayes minimum risk classification, when gix value is maximum, we can take the corresponding decisions. Basically, we have to maximize those functions. Out of this possible, this option that we have two functions here, we can explore the first one, this one. Okay, we can explore the gix will be probability of x given omega I into probability of omega I. Okay, now this is nothing but called discriminant function. When we try to maximize something or minimize something to take some decision accordingly, this gix is called discriminant function. Since we are saying that we will have this, we'll use this function as my discriminant function, right? Now this gix is probability of omega I given x, and this one. Okay, now can we take any function f? Can we put this one into inside any function x, f of x, like take this one. this GIX. This function f has to be monotonically increasing function. This function f has to be monotonically increasing function. Such that if it is monotonically increasing function, that means if probability of omega I given x is greater than probability of omega j given x, then we can say then f of probability of omega I given x will be greater than function of probability of omega j given x. This is the property of your monotonically increasing function. Now we are interested in maximizing these values. So when GIX is maximum, then f of probability of omega I given x will also be maximum. Okay, and we also know that this probability of omega I given x, this internal value, this value is also given as probability of x given omega I into probability of omega I. This is also given by this one. Okay, now we'll simplify this one. We'll convert this function again. Now suppose this f, I am applying the log function to function f. Okay, so this ln of probability of omega I given x equals to, so ln of this probability of this x given omega I, correct, plus this ln of p of omega I. From here we are applying this function. So the final gi of x will become ln of p x given omega I plus ln of p omega I, and this is what it is called your discriminant function. We'll now see for any given variable, we know that for some single variable, the normal distribution value is given by some function. If you guys remember for the normal distribution, so suppose this is a normal distribution curve, right? If you remember on the machine learning, this is a normal distribution curve, and the middle will be having this mu x. Okay, and here you'll be having x. Here on the y-axis you'll be given probability of x. Okay, and if you guys remember the formula of this curve, it will be 1 by under root 2 pi sigma multiplied by e to the power minus x minus mu square divided by 2 sigma square. Do you guys remember this one? This formula, everyone? For the normal distribution for a single variable. From here we can say that this sigma square, So here, how the spread of the data will be described or explained. So it will be explained by your sigma square, right? So when the sigma square value, this value is low, this means the graph will be narrower, means variance will be less. And when the sigma square value is high, that means graph will be more wider in this case. Correct? Now, is it fine, everyone? G function, yeah, correct. Yes, boss. Now, since right now we are discussing about feature vectors. Feature vectors means we'll be having multiple features, say in any visual signal, say image, the type of distribution will be multivariate. Correct or not? It will not be a single variable. There will be multiple variables. So let's say we have some d-dimensional feature vector. D-dimensional feature vector, where this x will belong to d dimension. Okay, in that case, guys, this probability value or this value will be given by 1 by 2 pi to the power d by 2, okay, into determinant. Determinant, this is nothing but determinant, this is not summation, this is determinant, this value to the power half, and e to the power we can write minus 1 by 2 x minus mu transpose, and determinant to the power minus 1 into x minus mu. This is in case of multivariate normal distribution, where we have more than one variable. Here in this case, can you see the variance is replaced by the covariance of feature vectors. Covariance of feature vectors. Okay, so the conditional probability distribution for any given d-dimensional feature vector d can be written as probability of the conditional probability. I'm saying conditional probability distribution. This is the simple distribution, probability distribution. The conditional probability distribution for any given feature vector x, said that it belongs to some class omega I. This kind of distribution will be given as 1 by 2 pi to the power d by 2 e to the power minus half x minus mu I transpose covariance matrix x minus mu I. Here, when I say determinant, it means this value is nothing but this value is nothing but a covariance matrix computed from all the feature vectors for class I and mu I. Sorry, for class I. Okay, for any class I. And this mu I is nothing but it is the mean which is computed from all the feature vectors for class I. Okay, when you calculate the variance, you will have some scalar value, correct? When you calculate the covariance, the final value will be
Matrix.
this one, some number only, correct? Scalar. But this covariance will be a matrix. This covariance will be a matrix. So that's why here it's a matrix and I am finding the scalar value and giving it in power 1 by 2. I means it is under root this one. It is the same one, right? Under root this one, or we can take the power half. It is the same thing.
Sorry, can you come again, please?
Which one?
No, I didn't get the part. Like it's a covariance matrix. So
Okay. So see, when you say covariance matrix, how do you find the covariance matrix? Covariance of x and y. How do you find that? If you have covariance of y, x and y, it means x and y, two features you are having, right? It means you will find this one, variance of, I mean, say, you can say covariance of xx, covariance of xy, right? Covariance of yx and
YY.
covariance of yy. This covariance of x and x is nothing but a variance of x. This covariance of yy is nothing but a variance of y. And you have to find the covariance of x and y. You have to find the covariance of y and x. And we put them all into the form of matrix. Right? Similarly, if you have to find the covariance of x, y, and z, it will be 3 cross 3 matrix, right?
yeah.
Correct? And same thing, we are putting it here. Here and here. Now, this mu y was the mean of all the classes, right? Now, we know since this g value, the determinant, we are trying to find the determinant function under multivariate normal distribution. Then again, we'll come to the determinant. Now, determinant, this gi of x was given as ln of, you remember, probability of omega I given x plus ln of omega I. Sorry, probability of omega I. Yeah. Okay. Now, can we replace this entire value with 1 by 2 pi to the power d by 2 into this covariance of I to the power 1 by 2 into e to the power all minus half into x minus mu I transpose this covariance matrix x minus mu I. We can replace all that value with this value. This value is the same value. In case of multivariate normal distribution, I can get the conditional probability. Basically, we are discussing with conditional probability, right? So for the conditional probability distribution, we can replace, we can take this value from here and we can put it here. The same thing. Correct? So our gi of x, this determinant function gi of x will become how much? Minus d by 2. If you solve it, you will get it. Minus d by 2 ln of 2 pi minus 1 by 2 ln of this determinant minus 1 by 2 x minus mu I transpose into, this is transpose, okay, into this covariance matrix to the power minus 1 x minus mu I plus ln of probability of omega I, this part. If I write the determinant function, because we are taking the log, and when we expand this, when we take the log, it will be off, right? And At the same time, we are taking the log of the two terms, ln of a into b, right? Correct, guys? So it will be ln of a plus ln of b. Equal to the logarithmic, conversion. So that's what we are doing here also. Now tell me one thing, this term, when it particularly talk about this term in the equation, this is nothing but independent of class. Can you see that? Independent of class. Correct?
Vivek,
So
maybe I missed it. What is the dimension?
which one? This is the
D.
d dimension, no?
D
This is the
dimension.
dimension.
Okay.
Yeah, it means x belongs to d-dimensional feature. X is a d-dimensional feature. D-dimensional feature vector of feature vector. Okay. Now this term, this particular term is independent of class. So we can also say that this particular term does not contribute to classify any class. Does it contribute? Can you see any omega I term here or I term here? No, right? Correct. So this will not contribute to any of to classify your feature vectors into any of the classes. Correct. And because of that, what we will do here, we will remove that term. We will not use that term since it is not contributing. So it's fine. We can neglect that. And finally, we can say that gi of x can be given as minus 1 by 2 ln of minus 1 by 2 x minus mu y, minus 1 by 2 x minus mu y transpose, right? Transpose into this covariance matrix I to the power minus 1 means inverse x minus mu y and plus the remaining term, this one, ln of p omega I. And this is the determinant function that we use in case of multivariate normal distribution. This is the function that we use. So now, what is the significance? Okay, what is the probability that what is the probability of this feature vector x given we will get given it belongs to some class omega I? We have this kind of probability that we derived by using uh, class conditional probability. Basically, you can say we have been given this kind of thing, right? Now this feature vector x is not a single variable. It is having a lot of other variables, lot of features. That's why I'm saying this x belongs to d-dimensional feature, right? And in that case, we have to maximize this probability that this x will belong to some class omega I while the training phase. Because see, in any model development, in while solving any problem in data science, machine learning, deep learning, we are basically having two phases: training and testing. Training and testing. While training, we have to find what is the probability that x will belong to omega I. While testing, the same thing will be changed. What is the probability that this feature vector x will belong to some class omega I while testing? Correct or not, guys? That's what we do actually, right? I mean, when you are training some algorithm, I mean, correct or not? Are you getting, guys? While training, while testing, any algorithm,
Yes.
while training, what we have to do actually, what algorithm does internally, it is finding the probability of any feature, any given feature vector x, which is belonging to given, it is belonging to y. Means while training, this thing will be given, this classes will be given, but while testing, only the feature vector will be given, and you have to find the classes, corresponding classes, in which class it will belong to. For that, I am interested in finding the probability, right? When we have this one, when we have the probability of x also, when we have the probability of classes also, we can find this one also, right? This is fine according to the Canisa probability based theorem. By using that, we can easily find that. Yeah. So that's why, and again, we have to minimize this. We have to maximize this term, right? So that your training will be better. Your algorithm will be trained more efficiently, more accurately. And when it will train more accurately, when you will try to increase, maximize this term, this discriminant function, then your algorithm will be more accurate, right? And that's what we are trying to do here. This is nothing but determinant function. That's why we are interested in finding the determinant function actually. Okay. And the way we derived the determinant function earlier, I mean, few hours back, I mean, half an hour back. So we were taking all these terms into consideration. Okay, and the GIX is nothing but the combination of this one, this probability plus given some probability value of omega I. And since I'm saying this x, feature vector x, it is not a simple linear regression where this one, what do you say, one independent variable and one dependent variable. It's not like that. We will be having multiple features. And that's why I'm saying this x will belong to d-dimensional feature vector. And in case of that, we are not interested in finding the variance. This variance will not work because this is for univariate, single variant, single variable. We are discussing about the single variate, distribution, probability distribution. But in real time scenario, we'll be discussing with multivariate scenarios where you'll be having a number of features, a number of different variables. And in those cases, what we need to do is we need to uh, find the distribution, probability distribution for multivariate, right? We found that multivariate. Now we also know, according to this formula, we will find the conditional multivariate normal distribution. Okay, and after finding that, we'll find the determinant function through which we can basically maximize this function to get the algorithm more and more accurately trained on the data. And that's what we are using this. We will be using this. Not only this one, there are a lot of different ways to train that algorithm. Okay, this is one of them. Okay, clear?